Well, hello, welcome back. Um, this is Descriptive Physics, and the topic we're going to be looking at now is vibrations and waves. So this is the beginning of the third part of our course. The kind of sums up together as well, vibrations, waves. We'll talk about sound next time, and beyond that, we're also going to get into electricity and magnetism in this part of the course, which has a lot to do with waves. So to start out with, let's just talk about some vibrations and see what we're getting into. So first off, vibrations is essentially just a movement that repeats in time, or like a wiggle, some kind that just sort of repeats itself. And it turns out vibrations are very common. Anything from sound is a type of vibration, water, waves, ocean waves, ripples in ponds, light, many different things are examples of vibrations, and vibrations producing waves beyond that. So vibration itself is essentially just kind of a wiggle. Vibrations can lead to waves when the thing that's wiggling starts to move or make wiggle, those kind of movements extend through space in some way. So a wave is essentially just a vibration, but that vibration is in some way sort of extended through space as well. It's not just changing in time, it's kind of moving through space beyond that. So again, some examples of waves, light waves. In the last section of the course, we talked a little bit about radiation and radiative heat. And I told you a little bit about waves then, just so that we could kind of understand a little bit about light. But yeah, we mentioned that light is a wave, and it has different wavelengths, which we'll talk about more in this section too. So there's various examples of light waves, radio waves, infrared waves, and visible light waves, and there's also microwaves, X-rays. Those are all examples of electromagnetic waves. It turns out that light is a type of wave that doesn't actually need a medium to propagate, meaning there doesn't have to be anything there in order for a light wave to travel. Another way of saying that is essentially that light can propagate in outer space where there is no stuff, there's no air, just essentially a vacuum. Another very common example of a wave is a sound wave. And a sound wave is technically what you call a mechanical wave, and it needs a medium to propagate, such as air, the air between me and the receiver, the microphone, is needed in order for the sound that I'm producing to actually propagate to that microphone. So sound won't propagate in outer space where there is no air, it's just a vacuum. Okay. So some very basic properties of vibrations, and also waves as well, because waves are just vibrations essentially extended in space. But vibrations, essentially, there's another term that we use sometimes called an oscillation. And an oscillation and a vibration are very similar sort of things. For our purposes, an oscillation is essentially a vibration that is symmetric. So something that's moving kind of moves the same amount up and down, or the same amount up as it does down, or the same amount left as it does right, depending on how it's vibrating. Right? So an oscillation, we can basically think about it as another way of saying vibration. It's just the term oscillation often is used much more in physics when we're talking about physical phenomenon. Yeah. So, one fundamental property of an oscillation or a vibration is the period or the time that it takes the object or the medium, whatever it is that's vibrating, the time that it takes for it to kind of go through a full oscillation, or sort of a round trip. You want to think about it that way. So, a very common example of something that oscillates is a pendulum. And a pendulum is just a weighted object that's attached usually by a string to some fixed point. And if you just let that object hang at rest, somewhere like this pendulum set up here, right? Just let it hang, it's not going to do anything, there's no vibration, there's no sense that it's oscillating at all. But what we do with the pendulum typically is you pull it off to one side, so we just displace it from its kind of rest position, and then if we release it, then it's going to oscillate back and forth around that rest position, what we call the equilibrium position. So the period is the amount of time that it takes for this mass to move essentially back, or one way, and then move back. Right? So it goes through one full cycle. So start here, you come back, there's one, there's two. And the period is just the amount of time it takes to do that. So being an amount of time, it's measured in seconds usually. And, you know, as an example, if you have a pendulum and it takes that pendulum 2 seconds to go through a full oscillation, just start at, say, the peak on one side, go all the way to the other side and back again. That takes 2 seconds. You'd say the period for that oscillation is 2 seconds. Pretty straightforward. The fact that pendulums oscillate in this very nice manner was utilized for these kind of grandfather clocks, which are the pendulum clocks, where they use a pendulum that's swinging back and forth at a very steady pace. So whatever its period is, you can utilize that to essentially tick along seconds. So a related property, very related property to the period of an oscillation is what's known as the frequency of the oscillation. The frequency is exactly the inverse of the period, or essentially 1 divided by whatever the period of that oscillation is. So in words, the frequency is the number of times an oscillation occurs per second. And as an example, if we, well, just like in the last slide, if there was a pendulum, say, and its period was 2 seconds, meaning it took 2 seconds to go to one side and come back, its frequency would be 1 divided by 2 seconds, or 1/2 of an oscillation per second. That would be its frequency. And that unit of oscillations per second, or how many times something oscillates per second, is shortened and called, well, given a new name, as the physicist who, or one of the scientists who study this sort of thing, hertz. So an oscillation per second, we just call a hertz. Hertz or hertz. I think it's plural. So 1 hertz is 1 oscillation per second. So these are essentially, the frequency and the period are essentially 2 ways of measuring the same thing. It's essentially how quick is the oscillation, right? How long does it take for that oscillation? Okay, so then another fundamental property of oscillations, vibrations, is what's known as the amplitude of an oscillation. And the amplitude is a measure of the distance, or sometimes just the kind of amount of change, from the equilibrium position. So in the case of that pendulum, the amplitude of this oscillation is measured as however far, maybe in inches or in feet or typically in meters, that mass moves away from the equilibrium position. So if it's at rest right in the middle, the amplitude is that maximum distance it moves away from the equilibrium. So we can measure the amplitude on the right side, as is shown here. The amplitude we could also measure on the left side if it goes, we wait for that pendulum to swing all the way to the maximum on the left side. So amplitude doesn't really care which side of that equilibrium you measure it from, because it's just saying how far absolute distance does our oscillation move from the equilibrium. So I said another example of oscillations or waves are water waves. This is a pretty rough picture of some water waves. It's sort of idealized. Usually it's a little bit more choppy than this. But if we look at this sort of idealized water wave, where the wave peaks up and goes down and up and down, we get these we call peaks and troughs in the water wave. You could imagine that if there were no waves there, then there wouldn't be any peak, there wouldn't be any troughs, and the water would be at its equilibrium position, which would be right sort of in the middle of those peaks and troughs, right? So that line in the middle is drawing, the dashed line is the equilibrium position, and that's, say then, that the amplitude of that water wave is measured from that equilibrium to the peak of the wave. You can also measure it to the sort of the middle, the trough of the wave. But it's just the maximum displacement that our material or that object is moving from the equilibrium position. Okay. So, waves in general, remember, essentially just vibrations that cause some sort of movement to extend in space. So now we're not just oscillating in time, there's a movement, there's an oscillation in space as well. And those properties of vibrations, the frequency, period, amplitude, those are all also, in addition, they're also properties of waves too, because waves are essentially just a subcategory of vibrations. Something to keep in mind is that all waves will carry energy, or transfer energy in some way. Right? So we already talked about in the last section how light waves, and particularly infrared light waves, will carry heat. Right? That's one way that heat is transferred is through radiation, and that's heat energy carried from or carried by infrared light waves. But all waves will carry energy: water waves, sound waves, radio waves, all waves. Right? So these are all just examples of different kinds of waves. One that we haven't talked about directly is you can produce a wave if you just attach, say, like a string to a wall, or have somebody else hold one end of the string, and you take the end that's not attached to the wall and you just start wiggling it up and down. What you'll see is that vibration, that oscillation that your hand is doing, produces a wave that travels along the string. So this is just another example of a wave. And so there's actually, turns out there's two basic kinds of waves. And the differences amount to whether or not the material that the wave is traveling through, so like water or water for water waves, or the sound, air for sound waves, whether that medium is moving in the direction that the wave travels or perpendicular to the direction that the wave travels. So those are the two basic types of waves. So the first kind we're going to look at here is what we call transverse waves. And transverse basically means across or perpendicular to. So the transverse waves are waves where the movement of the material of the wave is actually perpendicular to the motion the wave is traveling, or the direction the wave is traveling. A very nice example of a transverse wave is that same sort of picture that I was just talking about, where you have a string attached to a wall on one side, and if you oscillate the far end of the string, what you're going to do is produce a wave along that string. But really, the string is the medium that the wave is traveling along, and the string is actually just moving up and down. Right? The string's not moving left or right. The string's going up and down because you're moving the string up and down. But the wave is traveling along the string, and say it's away from your hand and towards the wall. Right? It's very easy to see this if you don't continually oscillate a string like that, but you just take a string and flick it up really quick, and then come back down to your sort of equilibrium. What you'll see is that you created just this one sort of crest, and that crest will travel from your hand towards the wall. So the picture here again is just showing that the vibration or the movement of the rope is up and down, but the movement of the wave is actually left to right here. Another example of transverse waves are water waves. So the water waves, they're like the ocean waves that sort of come up to the shore. It's not actually a bit of water that started way out and is moving its way in. The water itself, or the ocean, is really just moving up and down, but the ocean wave is moving into shore, say, or out of shore if it reflects back. It's a little bit more complicated than that in the ocean waves, because the ocean waves are going up and down, but they're also kind of going in a circular motion. But again, the water molecules that make up the ocean, they're not really moving overall in the direction the wave is traveling, moving essentially up and down and perpendicular to the direction the wave is traveling. So let's take a look. So another nice way of making transverse or different kinds of waves is actually with the slinkies. If you have a slinky, then stretch the slinky out and attach one end, and it's a very nice medium for seeing different kinds of waves. This is just a simulation, but you get the picture. So when you start to oscillate one end of that slinky, what you're going to do is you're moving the medium up, bring it back down, and that movement up and down is going to go ahead and travel along the slinky, right? So the transverse wave is the slinky's parts of the slinky, or the medium, the metal that makes up the slinky is moving up and down, the wave's moving left and right. All right, so another interesting example of a transverse wave, a wave where the thing that's making up the wave, the material of the wave, is moving up and down, and the wave's moving left and right, or it doesn't have to be up, down, left, right, as long as they're perpendicular to each other, is what we just call the wave at, say, like a baseball stadium or any kind of sports event. This is a popular thing to do, sometimes when the crowd is bored or sometimes when they're excited, it doesn't matter. But you've probably all seen it, where people in the stadium, one sort of section of the stadium stands up and then sits down together, and the people to this side of them, left or right, then will stand up and they'll sit down, and then the next sort of people stand up and sit down. And what they're doing is producing a transverse wave, where the medium is the people. The people are standing up and sitting down, but the wave is traveling along along the stadium, right? To the left or to the right, or counterclockwise or counterclockwise. Let's see. So this might not be so easy to see in this video, but if you go to the link or just look up the wave at a stadium and see well, essentially people just standing up and sitting down. The point is that this is a transverse wave where the people that are making up the material of the wave aren't moving left and right, they're just going up and down, but the wave's going left and right. Alright, so that was the first kind of wave, the first type of wave, transverse waves. Remember, transverse means the motion is perpendicular to the wave motion. The second type is longitudinal waves. So this is essentially the other kind, where the motion of the material that makes up the wave is actually parallel to the motion of the wave. So in this case, it's not, you don't see that same sort of peak and trough characteristic of waves as easily, because for transverse waves, it's not the medium moving up and down from the equilibrium, it's a sort of compression and a decompression of that medium. So, if we look at the picture up here, it's essentially a picture of like a slinky, where again you can use slinkies to make both transverse and longitudinal waves. For a longitudinal wave, you take a slinky and attach one end of it to something, or have somebody else hold one end of it, and then we're essentially making compressions and decompressions, also called rarefications. It's an odd term, but rarefication is essentially the opposite of compression. It's a decompressed area. But with a slinky, you essentially take one end now and then push it in and pull back. And what you've done is you created a compression in the slinky, compressed the rings of it at that point, and what you'll see is that that compression essentially travels down along the slinky. So the motion of the slinky, or the motion of the metal that makes up that slinky, is actually going left at one moment and then coming right at another moment. So there's actually, the motion of that slinky is actually left and right along the axis of the slinky. And this is a longitudinal wave because that motion is in the same direction that the wave is traveling, right? So the wave is essentially that movement of the compression and the decompression, or the compressed areas and decompressed areas. So for a longitudinal wave, the amplitude is basically a measure of the peak compression of the medium. So how compressed does it get? Right? So if I have that slinky and I push in a bit and then come back out, that's going to be a fairly small compression, so a fairly low amplitude for that longitudinal wave, versus if I push in really hard and come out quick, then it's going to be a very high compression, a very large amplitude of that longitudinal wave. A very important and one of the most common forms of longitudinal waves are actually sound waves. So sound is propagated by essentially compressions and decompressions or rarefications in the air. So the air is the medium that the sound travels, and the motion of the air, that's the medium that's making up that wave, is always just back and forth. Well, if the sound is traveling, say that way, the motion of the air is left and right, and the sound is actually traveling in the same direction, or along in parallel to that same motion. So this little picture here at the bottom is showing essentially a speaker producing sound, and what it's doing, we'll look more closely at sound later, but what it's doing is essentially has a cone, and that cone is moving in and out, and as it moves, say, out, it's compressing the air, so it's causing this compression, and that compression starts to travel out, starts to travel away from the speaker, and then it pulls back, so it causes a decompression or a rarefication, and then that motion keeps continuing outwards, so you have this compression place for this sort of compressed area, and then a decompressed area, and then it pushes again, and it forms another compression area, and so you get this wave, which is the compressed and decompressed area, areas of air, volumes of air. And we can still visualize a longitudinal wave as this same sort of like sine wave. Where we're drawing here is the increase and decrease in pressure. So for air, right, when that speaker pushes out, it increases the pressure, it compresses the air, right, and it causes this peak in compression. And then when it pulls back, it decreases the pressure, and it causes this sort of trough in the pressure. So the sort of same amplitude can be visualized, but it's just, again, it's for a longitudinal wave, it's a measure of the compression of the medium. So let's look at an example or a visualization. So again, with the slinky, right, like I was telling you, if you take that slinky and you push it and push in, you're causing an area of compression, and that compression travels down the slinky. And again, the important point that this is a longitudinal wave, meaning that the compression, the motion of the wave is down along the slinky. The motion of the slinky that's making up that wave is along that same axis. Right. So I'm not really used to seeing sound as a wave. Mostly because we don't see the air, so we don't see the movement of the air molecules. We don't see the compression and the decompression, or the peaks and the troughs and the pressure. But you can visualize or see, in a way, sound. For instance, by placing a candle next to a pretty powerful speaker. Right, the speaker, the cone of the speaker is moving in and out, so it's compressing and decompressing the air in front of it, and that compression that is translating as a wave motion, so the compression sort of propagates out away from that speaker. And so you essentially see that as a movement of that candle. It's like the air that's moving, the air is moving back and forth along the axis of that speaker, and you can see that in the movement of the candle. So you see that speaker cone moving in and out, it's compressing and decompressing the air, so it's moving the air molecules back and forth, and that movement is translating through the air, propagating as sound, and you have a much higher frequency of movement, or a quicker oscillation, you get quicker movements in the air. This video has some other stuff going on, but I just wanted to use the visualization as seeing the air actually moving. But keeping in mind that this is, again, this is a longitudinal wave where the medium is the air, and that medium is moving back and forth. It's not necessarily, it's not the air moving from the speaker out to the candle. The air itself is just essentially moving back and forth in place. But the compression that cone makes when it pushes out, it compresses a bunch of the air together, and then that air sort of moves back to where it was. But that compression is actually what is sort of making up the wave, and that compression moves away from the speaker. All right, so we talked about basic properties of vibrations, that being period and frequency, which essentially are two ways of talking about how quick an oscillation is or how rapid it happens. And then amplitude as in how far an object or a medium is displaced from its equilibrium. Or in the case of longitudinal waves, how large the compression is. That's sort of the amplitude of the longitudinal waves. So another property of waves, any wave, is what we would call its wavelength. And that's basically, it's sort of what it sounds like. It's a measure of how long a wave is. So in the case of transverse waves, it's pretty maybe easier to see. The wavelength is essentially just a measure between crests of the wave or troughs of the wave, so peaks or the bottoms, the tops or the bottoms, right? So in the picture here, the wavelength is indicated as the distance between the troughs, or sort of the minimums of that wave, right? So you go from one minimum to the next minimum, that distance is the wavelength. You could also measure it from the crests, and I would just measure from one crest to the next crest. That's also the wavelength. It would be the same distance. In terms of a longitudinal wave, it's essentially the same sort of thing. We're measuring the distance between the peaks of that wave. And in the case of a longitudinal wave, it's the peaks, sort of the peak compression areas. So if you measure from the most compressed area and move along the wave to the next most compressed area, that distance is a wavelength, right? That's the wavelength, that longitudinal wave. In terms of like the water wave, right? Again, so talking about the speed of the wave, or the wave speed, two ways of saying the same thing, is again just essentially what it sounds like. It's the speed at which the wave propagates, or which the wave travels. Here are just some examples of our kind of most common sort of waves. Right, we have sound waves, and the speed that sound travels varies a bit depending on whether you're at sea level, whether you're up behind the mountains. So it depends on the pressure of the air. Depends a little bit probably on the humidity level. But on average, the speed that sound travels through air is about 330 meters per second, or roughly 725 miles per hour. So pretty darn fast. Right? If I say something, the fact that speed travels the sound travels that fast, it almost seems like it doesn't take any time really for the words that I speak, between the time that I say them and you hear them. Right? Usually because we're pretty close to each other, so it seems almost instantaneous. But we'll see an example in a few slides of where it's very noticeable that sound actually takes some time to propagate. So one of the other most common types of waves is a light wave, electromagnetic wave. And at least in vacuum, light travels at about 300 million meters per second, so incredibly fast. That translates to about 670 million miles per hour. So ridiculously fast. Incredibly, way faster than sound. Pretty much faster, it's about as fast as anything ever goes in the universe. But I think we'll talk about that later in the course. And compare that to, say, the speed of an ocean wave. Right? Ocean wave, it can vary quite a bit, but a typical ocean wave maybe travels at about 6 meters per second, or something like 14 miles per hour. And you can kind of get a sense of that. You're just into the ocean, and you watch the waves roll in. They're sort of going at the speed of maybe a slow car rolling through a neighborhood or something like that. Right? So 14 miles per hour seems about right. And here we just have a picture of, ocean waves, right? People surf along ocean waves. And also a picture of a jet that's actually going pretty much as fast, or just a bit faster than the speed of sound, right? And it turns out that ends up creating what's called a sonic boom, and we'll say why that is sort of the very end of this lecture. Okay, so we've talked about, right, the frequency, and remember frequency is very similar to saying period, but in terms of physics, and usually in terms of calculations, and we're using mathematics, frequency is often the thing that comes into equations. So it tends to be the thing we talk about more often in physics versus, say, the period or something. But the frequency of a wave, its wavelength, and its wave speed are all directly intimately related with each other. So these are essentially three different ways of showing the same thing. Three ways of writing the same equation. The first one here shows that the wave speed, or the speed that a wave travels, is going to be equal to its wavelength multiplied by its frequency. Another way of saying that is the wave speed is proportional, or the speed of a wave is proportional to its wavelength, and it's proportional to its frequency. So you can measure wave speed in something like meters per second, right? We were just talking about wave speeds, meters per second, miles per hour, right? A speed. If you rearrange that relationship a little bit, then we get that the wavelength is proportional to the wave speed, but inversely proportional to the frequency. So the wavelength, again, is measured in, say, like meters, or maybe feet, or inches, some distance. And then finally, the last way of expressing this relationship, right, all three ways of saying the same relationship, is that the frequency of a wave, or how quickly the oscillation happens, is proportional to the speed of that wave, and inversely proportional to the length of that wave, or its wavelength. And again, frequency would be measured in inverse seconds, or oscillations per second. And again, we call that hertz. So you can hopefully get some idea of why these things are related in this way. If you imagine, say, you're sitting in the ocean, and there's waves coming through in the ocean. They're propagating towards the shore. Maybe you're sitting on a surfboard out in the ocean. You're going up and down, right? So you could maybe measure the frequency of your oscillation. Say you go up and down, I don't know, once every, I don't know, this is going to be, I'm not going to be good at making up numbers on the fly. So just imagine there's a certain time that it takes you to go up and down, and that tells you essentially the frequency, right? But hopefully you can see how the amount of time it's going to take you to go up and down is very much related to the speed that the waves are traveling by, right? So there's like a wave, and if it goes through faster, you're going to go up and down faster, right? So that's why the frequency would be proportional to the wave speed, but inversely proportional to the wavelength. So if the wave is very, very long, then it takes, it's traveling at a given speed, but if it's much longer, it's going to take longer for that wave to pass you by, right? So even though it's going by at a certain speed, since it's very long, it takes you a while to get all the way through that. So that's why the frequency will be inversely proportional to the wavelength. Okay, so then just a few questions. You can try to check yourself here. Again, I can't really ask you to just stop really and ask your neighbor anything, but hopefully you can pause the video for a minute here and try answering some of these questions on your own. It's very helpful if you just write it down, write down your answer, and then you go ahead and play the video and we'll talk about the answers. Don't be worried if you get it wrong. Oftentimes when you're wrong, it tends to make you remember better why you were wrong, so then you might be correct in the future, right? So just taking a stab at some of these, if they seem very easy, that's great. If they don't seem very easy, that's okay too. Right? But yeah, so go ahead and pause, hopefully, and give that a try. Okay. So, I guess I didn't point out the picture as much, but hopefully you saw the picture down here at the bottom, where we have these ocean waves traveling along. There's this bird sitting on a post. The bird doesn't really matter in this picture. The point is that these are waves traveling along the ocean. And we're shown in the picture that the distance between the peak of one part of this wave to the peak of the next peak along is 2 meters. Right? That's the distance between crests, i.e. the distance or the wavelength. So the wavelength of this wave is 2 meters. We're also shown in this picture the speed, v, usually used for speed, or typically for velocity, but we're not going to worry about vectors so much anymore. So the speed of this wave is indicated as 6 meters per second, going left to right here. So there you go, that's the wave speed. Then the frequency of the wave, or the wave's frequency, remember from the last slide, we can calculate that as the wave speed divided by the wavelength. So I didn't put in units here, but it would be 6 meters per second divided by 2 meters, and that will give us 3. And the units would be 1 over seconds, or oscillations per second, or hertz. Right? So 3 hertz is the frequency of that wave. How quickly, how many times it goes up and down per second. That would mean that the period of the wave, remember the period is, I didn't say this explicitly, but since the frequency is equal to 1 divided by the period, it turns out that means also that the period is the inverse of the frequency. The period is equal to 1 divided by the frequency. So if you have one of those, you can always get the other one. So in this case, the frequency was 3 hertz, so 1 divided by 3 hertz gives us about 1/3 of a second. 1 divided by 3, 0.33. So the period is 0.3 seconds, about 0.3 seconds. So that's the amount of time it takes for this wave to essentially go from its peak down to its trough back to its peak again. Speaking about relationships for waves, or the different properties of waves, how frequency and wavelength and wave speed are related. I'm going to jump ahead real quick to talk about sound for a second, and then we're going to come back to this more later. So this is kind of a little sneak peek maybe. But as I've mentioned before, sound is a longitudinal wave, right? Meaning it's made up of essentially compressions and decompressions of air, and the air molecules are moving back and forth as the wave travels along the same parallel to that movement. So it turns out that the range of frequencies that humans can hear is essentially, it's about 20 hertz, or 20 sort of oscillations per second, all the way up to 20,000 hertz, so 20,000 oscillations per second. And looking back at that slide on wave speed, you see that the speed of a sound wave, the speed of sound in air, is about 330 meters per second. So if you put those two things together, we could find out that the wavelength, or the distance between those compression, or the compression in the air, the distance between those, as far as humans can hear, is going to be, well, the 20 hertz side ends up giving us a wavelength of 16 meters, or about 50 feet. So pretty long, or pretty widely spaced compressions. And then on the high side, the frequency of 20,000 hertz ends up giving you a wavelength of 1.6 centimeters, or about half an inch. So we can hear essentially sound as longitudinal waves, compression waves in the air, anywhere from the compression being 50 feet, compressions being 50 feet apart, to them being essentially about half an inch apart. It's a very wide range, actually, of frequencies and wavelengths. And again, calculating this wavelength is just going back to those relations where, given the frequency and wave speed, you can calculate wavelength. And then also, just to go a little bit more into that, where check out the hearing ranges of different animals. Right, in this picture here, you have the hearing range of humans is sort of given as this sort of standard area over about 20 hertz to 20,000 hertz. And above here is higher frequency, below is lower frequency. And right, you can just kind of see that's our hearing range, but there are some animals that have a wider hearing range than ours, but around that, it's like crocodiles, goes even further into the lower frequencies. Lower frequencies would be even longer wavelengths. Whereas like bats and dolphins don't hear in our frequency range, but hear in much higher frequency ranges. And again, much higher frequencies mean much shorter wavelengths. Yeah, and as you probably know, bats and dolphins both use what's known as echolocation. So they can actually use the fact that they hear sound waves at such a high frequency that they produce very high frequency noises. And since the waves are so small, then when they bounce off of things, you get a very it almost gives you sort of a picture of the object that you just bounced off of. And those frequencies, they come back, they hear them, and they can essentially, just using sound, can create a picture of their environment. This is also why I've never actually used this myself, but there's things like ultrasonic rodent repellent, which essentially just emit a very high frequency or a high above human range. So we don't hear it, but you see it in the chart. Rats have a hearing range that's above our frequencies. So if you emit sounds and that higher frequency range and very intense sounds, then it's going to be incredibly annoying to any animal that can hear those, so they won't want to be around them. And similarly, where the dogs or canines, their hearing range is similar to ours, but it goes also above ours into the higher frequencies. So that's why they have things like dog whistles, where you can blow on it and you don't hear anything, but the dog next to you might be howling because it actually hears a very high-pitched noise coming from that. All right, so some other things about waves that are very interesting is the fact that two waves, or more than multiple waves, can interact with each other. Or another way we would say that is they interfere with each other. So when you have, as an example, you see maybe waves in the ocean where one wave has come into shore and it's reflected off the shore, it comes back, and it encounters another wave that's coming in. Sometimes, when those waves hit each other just right, then they interfere what's called constructively, so they kind of add together and you get a very large wave where they hit. Other times, maybe if they hit at a different sort of what we call phase, then part of the wave might be coming back very high, where the other one's coming in very low, and they're going to kind of cancel each other out. So waves do this very interesting thing of interference, and there's two sides of the spectrum of interference. One is constructive, and one is destructive. So I guess the other thing to say is that that's a spectrum. There's a whole range in between being fully constructive and fully destructive. Right? So we'll just think about the kind of extremes where we have constructive interference, totally constructive interference, maybe, or fully constructive, and then destructive. So first, this constructive interference are when two waves kind of overlap each other, and they're what's called in phase. So in phase is essentially a way of saying that they're doing the same thing at the same time. So if we look at the picture here, there's the two waves on the top and the bottom, and you imagine if they're interfering, you can just kind of imagine that you're adding them together. And when we add them together, right, the top wave is rising up at the same time that the bottom wave is rising up. And then the top wave is falling down at the same time that the bottom wave is falling down. So they're doing the same motion at the same time. So when you add those two in-phase waves together, we get this reinforcement. We get this constructive interference happening, meaning that the sum of those two waves actually gets a peak that's, well, the sum of both of those. If it's the same amplitude for both those waves, then the amplitude of the interference wave is twice that, and it goes down that much too. So that's one sort of extreme, and let's see a demonstration of that. Right? So you see these are two waves being formed, one from each side. So one person is going to pull up on this material, and this is just essentially a bunch of pieces of maybe like wood or something like that, and they're all attached to the same a metal bar, so that when you pull up one, probably not metal, some kind of string or something to connect them all together. So when you pull up one, it pulls up the other one, that pulls up the other one, you can make this wave action. So at the same time, both of these sides of these of this apparatus are pushed up and pulled down, so we create this sort of bump. Right? And that bump is a transverse wave, because the medium is moving up and down, and the wave's moving right, left, or left to right. So we create this transverse wave, but they're in phase. They're both up at the same time. Essentially, they're going up and down in the same phase, so that when they hit each other, you actually see that they combine, and we get a much larger wave crest right in the middle where they interact. All right, so that was constructive interference, where we have waves combining and they're in phase. The opposite end of the spectrum then is what we call destructive interference of waves, and that is where two waves are combining and they're out of phase as opposed to in phase. So out of phase means that when the two waves being combined, the first one, say, is rising at the same time that the other one is falling. And then the first one, say, is falling when the other one is rising. Right? So they're doing the opposite things. Right? So when you combine two out-of-phase waves, essentially can kind of imagine adding up the heights of these waves and putting them together, they cancel each other out. So one has gone up, the other one's gone down, and the sum of them is just no change at all. So let's see an example of this one. So in this case, as opposed to the constructive interference, where both sides of this material were pushed up and down at the same time, one side's going to go up, the other side's going to go down, so they're out of phase with each other, and the waves are going to travel along, and you'll see that when they meet, they cancel each other out, and it's just flat right where they meet up. So right there in the middle, you get nothing, right? No wave. Okay, so just some more pictures on this in phase versus out of phase. For transverse waves, right? These regular sort of ocean waves looking things. There's a term I've just been saying when you combine the waves. The technical term is superposition, where you superpose one wave on top of another. And essentially, like I was saying before, you just kind of like add the heights of the waves up. If one's up above the equilibrium and the other's up above the equilibrium, then they add together. If one's up above the equilibrium, the other's down below equilibrium, they kind of subtract each other. So in the in-phase case, we add the two in-phase waves, and we get this bigger wave overall, larger amplitude of the wave. We can also imagine combining two longitudinal waves, and as long as they're in phase, then we're going to get the same thing. The compressions combine, and the total, or the combined rate, the superposition of those two waves, is essentially a wave with a higher compression or the sum of the compressions of the individual ones. And right, the opposite of that again would be that out of phase, where if there's, instead of rising at the same time and falling at the same time, we have one rising and one versus the other falling. They're doing the opposite of each other. Then you combine those two, we get no wave at all. We get a flat sort of equilibrium. And similarly for longitudinal waves, if you have this these compression, you think about sound waves, and if they're out of phase, meaning one compression overlaps with one decompression, then the sum of them is essentially nothing. Right? You're just a regular, no compressed areas, no decompressed areas, everything at the same sort of pressure. And just to point out again that these are the two sort of extreme cases. There's a whole spectrum where you go from totally in phase to totally out of phase. And going back, we have this this constructive picture where they're totally in phase. You can imagine moving from totally in phase to totally out of phase if you, say, take that bottom wave and just sort of start to shift it over to the right. As you shift it over, we're slowly getting out of phase, or we're moving away from being totally in phase. And then eventually, if you shift it over half a wavelength, in fact, these waves will become completely out of phase. But there's a whole spectrum in the middle there where they're not totally out of phase, not totally in phase, but there's this in-between area. So mostly we're just thinking about these extreme points where it's totally in phase, totally out of phase. Right, so let's see some examples of this interference in waves that are in phase and out of phase. For one, you can see interference in water waves, where, say, you take two objects and maybe drop them into a pool or a pond. Each object is going to create ripples, it's going to create waves emanating out from it. And where those two, if you drop two of them in, then you have ripples coming out from either of them. and where those waves intersect, where they overlap each other, they're going to interfere. So let's see an example of that. So here the guy's actually using these two sort of like bobs on sticks, and he's going to be just kind of oscillating one of them up and down in order to create continuous ripples, and then bringing the second one to oscillate up and down next to it. So you're going to create two of these waves, these ripples emanating out from where the bobs are going up and down, and we'll see this interference pattern. We don't just see, essentially you don't just see the individual ripples, that's circular ripples, you see the combination of those two where when one of the waves, say, is moving up and the other one is moving down, then they're going to interact or interfere destructively, and we'll get flat, sort of equilibrium, versus there's going to be other places where one of those ripples is moving up, the other one's also moving up, and we get these larger waves. Okay, so you got the one who's creating our waves emanating out here, and you just see the regular crests and troughs. But once you start taking the other one, it's not just the individual waves we see, but we see all these points where the two waves are intersecting, and at some of the points, essentially the water is flat, where there's destructive interference, and some of the points it's actually higher than it would be for either of them. That might be an example of he's talking about more than just water waves in this video, but that portion of the video, if you want to go look at it and actually listen to what he says there, it's probably be helpful to point it out. But I guess even pointing out when the video is paused, you can see these sort of emanating lines or rays of destructive interference, where the two waves are overlapping and we just get flat water. And then you also have areas of, well, in between that, and then constructive interference, where you actually still get these peaks in the waves, right? So that's the interference pattern right there. So another example of an interference, waves interfering, is when you have sound waves interfere with each other, right? So when you produce sound waves, just like the water waves, like waves rippling out from a point, if you say have two speakers, then each of those speakers are creating sound waves, or creating those longitudinal compression waves in the air, and those are emanating out from the speakers. Right? So just like there are interference patterns in the water waves, there's this interference pattern in the sound waves, meaning that there are going to be places, if you have two speakers set up, separated from each other, there's going to be places where those sound waves are going to interact destructively, and you're going to get hardly any sound at all. It's going to be very quiet. And then there's also places where you'll get the waves interacting constructively, and you'll get a louder sound. And so the video we're going to see is essentially someone's set up these two speakers, and they have a microphone, and just going to walk sort of perpendicular to where the speakers are, or along from one speaker to another. And as we walk through, the microphone was going to pick up the sound from them, and at points it'll be very loud, and you keep moving over, it'll be very quiet, almost nothing at all. And so we're sort of moving through this interference pattern. So
quiet now, so that the microphone would just pick up the sound from the speakers.
Essentially, we're going from these very loud interference, constructive interference places. You move over, you get almost complete destructive interference, and you get no sound at all. Right, so all he's doing is just moving back and forth in front of these speakers. And just like we saw those rays on the water ripples, these rays of these destructive interference areas, the same sort of things happening in the air too. We're getting destructive interference in these particular places, and as he walks through them, you get almost no sound. right? Because you get the destructive interference out of it. So a neat way to utilize destructive interference, or a cool example of that, is noise-canceling headphones, where basically what the headphones are going to do is they have actually a microphone outside of the headphone that picks up the sound wave that's coming in, and it doesn't stop that sound wave. That sound wave is still going to go through, but what it does is has another speaker set up on the inside that is just there to produce a sound wave that is exactly the same as the sound wave coming in, but out of phase, completely out of phase. So essentially, like, you think about it as like inverting that sound wave. So when that first wave comes in, like this external wave is coming in, that's what it picks up. It creates this inverted wave. This wave is completely out of phase with that external noise, and also sends that into your ear. So both those two things together, they're exactly out of phase. It's a much noisier wave than most of the ones we've seen, but that's noise overall. It's not these nice, pure tones. But as long as the speaker on the inside can produce a very close representation of the inverse of that wave, you essentially get complete destructive interference, and we don't hear any noise from the outside at all. Okay, so a couple of last things about sound. One is what's known as the Doppler effect, and not just with sound waves, we're going to talk about sound waves, where if you have, say, the source of a sound wave, like a siren on a fire truck, the frequency of the wave that you're going to hear, the frequency of the sound you're going to hear from that siren, depends on whether or not that siren is stationary, right? Whether it's parked somewhere, whether it's moving towards you, or whether it's moving away from you. So if it's stationary, the picture here we see on the left here, where the truck is at rest, it's putting off its sound waves, right? So it has some kind of cone generally, and that cone is just pushing, oscillating back and forth in order to compress and decompress the air. And it's doing that at the same rate, so it puts off these sound waves, and we see in the picture here, we're essentially just drawing or visualizing the compression areas of the sound, right? So the area where the sound is most compressed, or the air is most compressed, right? Another term for the peaks of those compression sound waves is called wave fronts, sometimes too. So we're seeing these wave fronts, right? And when the truck is at rest, it's emanating at one frequency, meaning one wavelength, and so the distance between those wave fronts, between those compressions, is the same. It's a certain distance from one to the next. So whether you're standing one side, the other side, it doesn't matter. The waves are emanating out in all directions, and they all have the same wavelength, and so you all hear the same frequency, the same pitch, essentially. However, when the truck is moving, say you're on the left side here, and the truck is moving away from you, then essentially, once the siren has emitted one wavefront, instead of being able to emit the next one to keep that same wavelength, the source is now moved a little bit away from you. So the next wavefront is a bit further away than it would have been if the truck was stationary, meaning that the wavelength is actually longer than it would have been if it was stationary. And if you look back, that means the frequency is actually lower. So if the source is moving away from you, what ends up happening is the frequency you hear is actually lower, or a lower pitch is another way of saying that. The opposite is true if the source is coming towards you, right? If that siren is coming towards you, it puts out that one compression, or sort of does that one compression movement, or puts out that wavefront. And before it puts out the next wavefront, if it was stationary, it'd be at that certain distance. But before it does that, it's already moved a little bit closer to you. So now when it puts out that second wavefront, the wavelength is less, right? It's shorter. So we have, when the source is moving towards you, it's actually a shorter wavelength. And again, that means a higher frequency. So Another way of saying that is that a higher frequency meaning like higher pitch sound. So you hear a much higher pitch sound when an ambulance or fire truck has its siren on, it's coming towards you, and then once it starts moving away from you, it sounds lower. Right? So this is an example of the Doppler effect. All right, and then the last thing about waves has to do with what happens when, also similar when source of that wave is moving in a way. We can create things like, well, the broad term is called a bow wave, but overall the idea is, say, like if you think back in that picture of that guy bobbing a ball up and down on the surface of a pond, if he was moving that bob along as he was bobbing it, then we start to get this picture like that diagram in picture A, where, and similar to the Doppler effect, where after that first bob is done, you create another wave crest or another wave front, but now it's moved along, so it's a little bit closer on the one side. You see this, it's closer, we have this shorter wavelength, and on the other side it's moved away, so we have this longer wavelength. So by having this moving source, the wave fronts are going to start to combine, or maybe start to combine, if the source is moving fast enough. So at first, if the source is moving just a bit, then all we're really getting is a higher sort of frequency on one side, a lower sort of frequency on the other side. If, however, the source of that wave is moving as fast as the wave fronts are actually moving, then you start to get this second picture, that can be, where the wave fronts on the one side are actually going to start stacking up on each other. So before, if the source of the wave is moving as fast as the waves, then at least in the direction that the source is moving, there's going to be no difference between the one wave crest and the next wave crest. And since, once one wave crest is like coming out on one side, the next one comes out right on top of it, right? Because the source has moved to that the next position. So we get this picture in B, where on one side they all start to stack up. And keep going with that idea, and in that picture in C, we start to see that if you have a source that's moving faster than the waves are actually moving, then you're not just getting a stacking up on that one point. Now, once one wavefront is emitted, the next wavefront is actually emitted past that first one. Right? And then that continues to happen. So what that ends up resulting in is essentially interference. You create interference in this sort of diagonal pattern, sort of behind the direction of that, or behind the movement of that source. And the faster that that source is moving, then the sort of skinnier that cone becomes. So it seems very complicated, but a really simple example of this that everybody has seen is if you ever look at a boat, speeding across the water, water wave, or the wave speed in water is fairly low, so when it doesn't take a boat going very fast in order for you to start to see this wake, right? And the wake is exactly that. The wake is this bow wave. The wake is the water waves that are being produced by the boat sort of bobbing along as it moves through the water. But since it's moving faster than the water wave, all of these wave crests are building up behind it and creating this sort of diagonal interference pattern behind the boat. So that's in water, pretty easy to see. It also happens in air too, except for the speed of sound waves is much faster than the speed of water waves. So it takes something going very fast through air in order to create this bow wave. But it does happen. as long as, remember, the speed of sound is about 330 meters per second, or something like 720 miles per hour. So once you get something moving that fast through the air, or in particular faster than that, then you're going to start to create the same idea. Is you're going to have like a wake behind that object, and the wake is essentially the interference of the air, the compression waves in air that are stacking up behind it. So the term that we use for that instead of regular bow wave is when it's in air, we tend to call it this shock wave. And again, since it's in air now, it's not just this two-dimensional sort of V shape behind like a boat moving through water. This is now a cone, it's a three-dimensional shape. And so as all of those wave fronts are sort of stacking up behind the object, typically like a jet airplane, those wave fronts are interfering constructively with each other, and you get this very large increase again in pressure, and then it drops back down really quickly. And we experience that as a sonic boom, right? This very loud just bang, right? And that's essentially an example of constructive interference happening because objects are moving faster than the speed of sound, or faster than the sound wave can travel. Okay, so I believe that's it for this lecture. I think this one might be been a little bit longer than intended, but probably still shorter than the actual lecture time is. So hopefully you stuck through it, and kudos to you if you did. The next lecture probably will be a little bit shorter. The next lecture is going to be on sound, and we're going to combine the next two chapters because we kind of got to jump ahead a little bit. So the next lecture is actually on sound, and we'll talk about music a little bit. All right, so see you next time, and I hope you're well.